Magnetism. It's going to be a review for the right-hand rules that we've discussed in class. What causes magnetism? Charged particles in motion. What demo did we do that demonstrated this? We had a power pack, and I hooked up 2 wires to the power pack to complete the circuit. Then I put a compass under the wire, turned the current on, and it deflected the needle. Here's a zoomed up picture of the same thing. The positive current is flowing in the wire this way, and the needle would point in this direction. It's aligned with the magnetic field created by the charges moving in the wire. The right-hand rule that shows us this is the one where we put our thumb in the direction of positive motion, and then our fingers will curl in the direction of the field lines. So put my thumb in the direction of the positive motion, and my fingers will curl in the direction of the field. So you can imagine this pencil being the wire. My fingers curl around the wire with my thumb in the direction of the current. Now, it's probably easier to see this if you look head on. I'm going to draw that diagram. If I view the wire from here, I can say that I'm looking right at the end of the wire. The current is coming towards me, so I put a dot as if it was the tip of an arrow approaching me. My thumb goes in that direction. If I put my thumb in this direction, my fingers will curl around in the direction of the field lines. There's no beginning or end to these field lines. They just make a circle. The variable for this magnetic field is the letter B. The compass needle underneath the wire aligns with that magnetic field, and that's what we're seeing here. What's going to happen if I put the compass on top of the wire? The needle won't be down here, the needle will be up here, and it faces the other way. The needle is aligned with the magnetic field going in the opposite direction. Now I've moved the wire below the compass, and the needle is going to point in this direction according to the right-hand rule for the creation of these magnetic field lines. So what happens if I turn the current off? There's no more positive current flowing. The needle will realign with the Earth's magnetic field, and that's what we saw in the demo. So we can ask ourselves this question: what is the direction of the magnetic field produced by those charged particles in motion? So we apply our first right-hand rule. First, put your thumb in the direction of positive motion. Then your fingers will curl in the direction of the magnetic field lines. Let's make a quick comparison between the electric field and the magnetic field. What causes the electric field? Just a charge. It's not moving, it's just a charge. The electric field is generated by that charge, and it spreads out from that point charge, radiating out into 3-dimensional space. A negative point charge looks the same, but the field lines are going in the opposite direction. These are 2 separate point charges, and we know the field lines go in those directions because we can put a positive test charge in the area and watch it move. With the magnetic field, we have charges in motion in this wire. It's positive current. Here, we can see that the magnetic field will make loops due to the right-hand rule. You put your thumb in the direction of positive motion, and your fingers will curl in the direction of the field. The magnetic field lines form loops without a beginning or an end, unlike the electric field, which has a beginning at the charge. Another way to look at this diagram is by imagining a slice through the board, and we'll see if the field lines go in or out. I'm putting a dot here, here, and here because the field lines are coming out of the board up here. And down below, I'm putting X's to represent the tail feathers of an arrow. So the arrow of the magnetic field comes out, around, and in. Yet another way of looking at it would be from the end. This view is represented here. I'm looking at the end of the wire. The current is going this way, so I put an X to represent that the current is going away from me. I put my thumb in the direction of positive motion, and my fingers will curl around in the direction of the field lines. These field lines get weaker the further away we go. How does this all apply to a regular magnet that we saw in the demos? Where the field lines emerge from a magnet, we call that the North Pole. Those field lines will loop around and they will enter the magnet. Where they enter the magnet, we call that end the South Pole. But those field lines don't stop there. They just continue on through the magnet. They create loops. There is no beginning or end to these loops. Now you might be saying, well, I don't see any motion in those magnets. Where's the motion? We have to have charged particles in motion. Well, on an atomic scale, there is motion, the electrons. Let's say we have an electron and it's spinning this way. The right-hand rule is based on positive motion. So we can picture a whole bunch of negative charges around the equator all going like this. If I want to use the right-hand rule to predict what's happening with the magnetic field produced by this spinning electron, I need to work with positive motion. If the negative motion is going this way, then this is the direction of the positive motion. Now we're going to think about this in 3 dimensions. I'm going to put my thumb in the direction of the positive motion, and my fingers will curl down through the center of the electron and emerge out the bottom. They're going to continue on and make a loop. If these field lines emerge at the bottom of the electron, then we know that that's the North Pole of the electron. If they enter at the top of the electron, then that's the South Pole. When electrons are in atoms, they go into orbitals, and electrons pair up in these orbitals, and their spins will be in opposite directions. That will cause the magnetic field to cancel. But in some atoms, some of these valence electrons are unpaired, and their magnetic fields will not cancel. These types of atoms can produce a magnet. Let's say we have an atom, and then another atom is nearby, and that's in contact with yet another atom. If we can get these atoms to align like this, then the material becomes a magnet with a North Pole and a South Pole. If the atoms are all aligned in random directions, the magnetic field will cancel out, and this will not be a magnet. What does all this have to do with the electromagnet? Again, we have our power pack, and when the current is turned on, the positive motion flow is going to produce a magnetic field. Each coil concentrates that magnetic field in the center and adds to the previous one to make a stronger magnetic field. The nail is made of metal, which conducts the field lines better than air. I'll zoom in on the coil at the end of the nail. Let's just look at one loop. The positive current is going this way. I put my thumb in the direction of positive motion, and my fingers will curl such that the field lines will be going in the nail and then out and around like this. We can probably see it better with a cross-sectional view. This is a slice of this picture. So this circle up here represents a cross-section of the wire up here. That circle represents a cross-section of the wire down here. The current is going into the board on top. So I put an X there to represent the current going into the board. I put my thumb in the direction of positive motion, and my fingers will curl around. On the bottom, I'm going to put a dot. That represents the current coming out of the board. I now put my thumb in the direction of positive motion, and my fingers will curl this way. So from this diagram, we can see that the field lines are coming into the nail on this end, making this the south side, and they're going to end up coming down the nail and leaving out of this end, making this the north side. Each one of these circles matches with the next loop creating a series of circles that overlap. So here we have the nail with the cross sections of each of these wire loops. And if I duplicate this diagram over here, when the field lines overlap, they end up forming a continuous path down the middle of the nail. And they emerge at this end and loop around to that end, making this end the South Pole and that end the North Pole. So just how does this electromagnet pick up a piece of metal? The paper clip is made of iron, which has unpaired valence electrons, but those atoms are all oriented randomly, and so the magnetic field does not add up, it cancels out. But when you place this metal near the magnet, then the magnetic field from the magnet causes these atoms to start to bend and wiggle and align with the magnetic field that it's producing. And so now it becomes a temporary magnet, and its North Pole will be attracted to the South Pole. When I turn off the current, these atoms randomly realign again. They haven't been stretched and pulled to the point where they can stay permanently as the magnet. They could be if we heated it up. Then they'd get hot and move around, and if we kept the magnet on, they would, and then let it cool down. If you let this cool down, it'll align and then stay that way as they cool. Then you'll make that a permanent magnet. Now for a second part of this review. What happens to a charged particle as it moves through a magnetic field? It will experience a magnetic force. The direction of this force is given by right-hand rule number 2. Here we have a magnetic field. The symbol for that field is B. Here we have a positive charge moving into that field. When the charge is in the field, we use right-hand rule number 2 to find the magnetic force acting on that charge. You put your thumb in the direction of the positive motion. You put your fingers in the direction of the magnetic field that's going into the board. And the force will come from the palm of your hand acting on the charged particle. I know all of this is tricky because it's all in 3 dimensions. That can't be helped. The magnetic field problems are all 3-dimensional. So you have to put your thumb in the direction of positive motion. Your fingers go straight in the direction of the magnetic field. That would be into the board. And the force comes out of your palm. We saw this right-hand rule demonstrated with the oscilloscope. We saw the light produced on the phosphor screen from a beam of electrons that was accelerated towards the screen. Let's say I bring the North Pole of a magnet to the side of the oscilloscope. I'm greatly exaggerating the uniformity of the magnetic field. The field lines come out of the North Pole and they curl. Some will go straight, and it's the straight ones that I'm looking at here. They'll eventually curl around too, but let's exaggerate it and make believe that they're just going straight. What will happen to that beam of electrons? We're going to apply right-hand rule number 2. You put your thumb in the direction of positive motion. Now don't forget, those are electrons. They're coming out at you. So which way is positive motion? It's going to be into the board. So you put your thumb into the board, your fingers in the direction of the magnetic field, and then there's going to be a magnetic force acting down on those electrons. That's what I demonstrated with the oscilloscope. When I bring the North Pole, the beam would be deflected down. If I flip the magnet around, the field lines are now going into the magnet on this end. I put my fingers in the direction of the B field, thumb in the direction of positive motion, which is into the board. You have to be a trickster to do this here. And the magnetic force is going to go up. And the beam will be deflected upwards. Make sure you use your right hand when you do this. I see kids use their left hand all the time, right? It doesn't make sense. You have to practice doing these magnetic field drawings and problem solving at different orientations. You're always going to be presented with a different viewpoint. Which direction will be the force acting on this charged particle? Put your thumb in the direction of positive motion, fingers in the direction of the B field, and the force will come out from the board. So we'll represent that force with a dot. The force is coming out of the board. Here's a different problem with a different orientation. We have a magnetic field. Those are dots. That means the magnetic field is coming out of the board. I have a negative particle moving down. What will be the direction of the magnetic force acting on that charged particle moving through this magnetic field? Positive motion is up. So my thumb goes up and my fingers have to go out of the board. And my palm pushes the particle to the right. The magnetic force is to the right. Now you might notice that everything is at a right angle, and that's the way it works. Let's do this one, and then we'll trace the path. So we have a velocity going to the right, and we have the magnetic field going inward into the board. The direction of the magnetic force will be towards the top of the page. Thumb, fingers, the force. Now what's going to happen if that force acted on a particle while it's moving to the right? This force will cause this particle to start to move up at an angle. And now the velocity will be off like this. If we once again use the right-hand rule, my fingers go into the board, thumb in the direction of positive motion, my palm will be pushing against the particle like this. Now that's going to cause this thing to continue to curve. And now the velocity will be in this direction, and the force will be in this direction. So what will be the path of a charged particle moving in a magnetic field? It's going to go around in a circle. Now there's a formula that was discovered when people were studying magnetism originally. F equals QVB. Something very important about this formula is that the velocity has to be perpendicular to the magnetic field. Notice that even if this particle starts to curve, if the velocity is this way or if the velocity is that way, it will still be perpendicular to the magnetic field because the magnetic field is going into the board. Notice that if there's no velocity, you don't get a force. So charged particles moving through a magnetic field will have a force on them. If the charged particle is just sitting there, you don't get the force. The units for the magnetic field are Tesla. Let's just say we had a magnetic field of 2 Tesla. That's a very strong magnetic field. Most magnetic fields are nowhere near that strong. The velocity is going to be 10 meters per second. And the Q will be 3 coulombs. Of course, we're not going to have normally charges that big moving around. But if you plug all this into the formula, what are you going to get? Because this is force, these units all have to work out to be newtons. And we get 60 newtons. Obviously, a Tesla is a derived unit from other fundamental units. So if we have newtons for force, coulombs for charge, and meters per second for velocity, the magnetic field would have to be newton seconds over coulombs times meters. It's a lot easier to just call it a Tesla. Now we're going to give this charged particle a mass and apply that to the curve. That curve is part of a circle. We have circular motion. The force, because of the right-hand rule, is always going to be perpendicular to this motion. That, therefore, is a centripetal force. Sometimes we put the letter B to represent magnetic force. So what causes the centripetal force? The magnetic force. We can say FB equals FC. The magnetic force is QVB. What's the centripetal force? You remember? It's mv squared over r. What is the radius of the curve of the path of the particle? That velocity cancels with the velocity squared, and we have mv over qb. This is a very useful formula. We are going to do applications like this many, many times when we study magnetism. But right now, I'd like to ask you, how much work do you think this force is doing to the charged particle as it moves around this curve? Do you remember what work is? Work is equal to a force times some displacement, okay? But you know, that force has to be parallel to that displacement. But look at the diagram. At any given moment, the particle is moving perpendicular to this force. The force is perpendicular. So everywhere we go, the velocity is tangent to the curve, and the force is perpendicular to the curve. So there is no work being done by the magnetic field because the force is always perpendicular to the displacement at that moment. But what if the velocity is moving at an angle to the magnetic field that's not perpendicular? You're going to have to break that velocity vector up into two components. Which of these components would produce a magnetic force? The y component is perpendicular to the magnetic field. The x component is parallel to the magnetic field. That will not produce any force. This one will. You put your fingers in the direction of the magnetic field, thumb in the direction of positive motion, and yeah, it's a perpendicular. The force will be in. This thumb is this way. It can't be in this direction. You have to outstretch their thumb when you use the right-hand rule. Now, what's going to happen actually is that the force is going into the board here, kind of drawing this in 3 dimensions here. And as it goes in, the force moving inward, coupled with that velocity going upward, will make it start to curve up. As it starts to curve upward, that is still going to be there. This velocity won't be affected by the magnetic field. And as this thing comes around, it's going to carry it forward, creating a helix. Some kids call it a spiral. It's not really a spiral, it's a helix. Where do we see action like this? Here's the Earth. We said earlier that due to the metal core and the currents of that metal, the Earth has a magnetic field. That magnetic field comes out here and goes in here, making the north pole of the Earth actually a magnetic south pole. The sun produces charged particles, the solar wind, that hits the Earth. These charged particles enter the Earth's magnetic field and they start to undergo circular motion. If a charged particle enters the magnetic field at an angle, it will undergo helical motion. They're going to start to curve around, and the magnetic field is closer together at the poles. It's weaker here, stronger here. That's going to make this helix start to get tighter and tighter. As the electrons get squeezed, they're dropping down to a lower energy level, and light is being given off. This is what we call the aurora borealis. The same thing will happen when the particles travel this way, and they start to form the helix, and they get tighter, they squeezed, and the energy is given off as light, and that's the aurora australis. Well, that's covering a lot of stuff, so let's summarize. Magnetic fields are produced by charged particles in motion. You can find the direction of the magnetic field lines by using right-hand rule number 1. Thumb goes in the direction of the positive motion, and then your fingers curl in the direction of the field lines. A magnetic force will act on a charged particle when it moves through a magnetic field. You can find the direction of that magnetic force by using right-hand rule number 2. You put your thumb in the direction of positive motion, your fingers in the direction of the B field, and the force comes out of the palm of your hand. The formula that goes with this rule is F equals QVB. We usually put the perpendicular sign under the velocity to remind us that the velocity must be perpendicular to the magnetic field. Sometimes we put a B as a subscript to remind us that we're talking about a magnetic force. Now, all this may seem like a lot, but believe me, it's only the beginning for magnetism. Don't fall behind.